Hi student friends, good morning to all. I welcome you all in this fluid mechanics lecture. In the last lecture, we have seen the viscous flow flowing through the pipe, and we have solved the problem based upon it. Right. So in today's lecture, let us see the next point, that is flow of viscous fluid between the two parallel plates. Right. So when the flow takes place between two parallel plates, viscous flow, when it takes place through the parallel plates, then what will be the velocity distribution, what will be the shear distribution, that we will see here. So in your notebook, write down the title first: flow of viscous fluid between two parallel plates. Flow of viscous fluid between two parallel plates. The analogies are similar to the pipe flow. Pipe flow मध्ये आपण ज्या पद्धतीने त्या ठिकाणी कॅपिटल आर घेतलेला आहे. Capital R is nothing but it is the total radius of the pipe, and small r, it was the distance from the center line, okay, towards the pipe. That was the small r. Similarly here, instead of capital R, the h is taken as the distance between two plates, and here small r च्या या ठिकाणी काय घेतलंय, y घेतलेलं आहे. The distance y away from this plate, that is nothing but it is y. Okay. Then velocity distribution, it can be given by this equation. You can note down this equation: u is equal to minus 1 upon 2 mu del p upon del x into h y minus y square. This expression is analogous or similar to the expression that we have derived for the pipe flow. If you remember the expression for the pipe flow, what is that expression for the pipe flow? U is equal to, for the velocity distribution, if you remember, yes, this is the expression that we have derived for the U is equal to minus 1 upon 8 mu del p upon del x into r square, capital R square minus small r square. So the expression that we have derived for the velocity distribution in a pipe, minus 1 upon 8 mu, and here this expression is minus 1 upon 2 mu. Instead of 8 mu, there is a 2 mu, and del p upon del x is common, and instead of r square, there was capital R square here, and minus small r square was there, and instead of that, instead of capital R, h is used there. Okay, hy minus y square, and instead of small r, y is used here. Okay, this is the expression for velocity distribution. And if you put, well, where the value of h will be, value of y will be maximum at the center. Okay, if you put here h is equal to y is equal to h, y is equal to, जर आपण h टाकले या ठिकाणी, or h by 2, here if you put y is equal to, जर y is equal to h टाकलं तर काय होईल या ठिकाणी, म्हणजेच या ठिकाणी वेलोसिटी काय असेल, y is equal to h म्हणजे या ठिकाणी h आलं, या ठिकाणी h आलं, हे झाले h स्क्वेअर मायनस h स्क्वेअर, मग h स्क्वेअर स्क्वेअर मायनस हे कॅन्सल होऊन जाईल, वी विल गेट 0. म्हणजेच काय, वेलोसिटी ॲट दिस पॉइंट ॲज वेल ॲज वेलोसिटी ॲट दिस पॉइंट विल बी 0. y ची जर व्हॅल्यू आपण 0 टाकली तर दिस विल बिकम 0, दिस विल बिकम 0, म्हणजे वेलोसिटी या ठिकाणी पण 0 आहे आणि या ठिकाणी पण 0 आहे. ठीक आहे. When we will get the maximum velocity, when we put h is y is equal to h by 2, h by 2 जर आपण या ठिकाणी टाकलं y is equal to h by 2, हे काय होईल या ठिकाणी, h by 2 minus h square by 4. Okay. So here it will become h square by 2 minus h square by 4, so it will become h square by 4. Okay, so this is the formula for getting the maximum velocity, and here also we get the parabolic curve because power of y is 2 here. Okay. So this is the, in the above equation, mu and del P upon del x are the and h are the constant in this equation. It means u varies with the square of y. म्हणजे ही जी velocity आहे त्याच्यामध्ये हा constant आहे, हे constant आहे, it is varying in this direction. Okay, so the u is directly related to the velocity y, value of y or square of y here. Hence equation is an equation of parabola. Again, it is a parabolic equation. Hence velocity distribution across a section of the parallel plate is a parabolic, as the power of y is square. So this expression can be shown diagrammatically like this. Here you can see this is the straight line and velocity. How velocity increasing here up to the center of the pipe, center of the plate, and again it will go on decreasing up to here. Okay, so we'll get your parabolic curve here for this velocity. Velocity will be minimum or zero at the boundary, and it will be maximum at the distance half of the between these two plates, half distance between two plates. Next comes the shear stress distribution. This is the formula for shear stress distribution. Tau is equal to minus 1 upon 2 del P upon del x into h minus 2y. What was the formula for the circular shear stress distribution? Does anyone remember? Do anyone? Tau is equal to minus del P upon del x into, yes, anyone? See there in the pipe flow, viscous flow through the pipe, त्याच्यामध्ये बघा टाऊची आपण इक्वेशन काय डिराइव्ह केलेली आहे किंवा लिहिली आहे या ठिकाणी. Tau is equal to minus del P upon del x into r by 2. Okay, I think you have been muted. You can unmute yourself and you can talk. So here note down this equation for shear stress distribution, as the power of this shear stress distribution, again it depends upon the y, and the power of y is 1, so it is a linear relation, and that's why the curve we get is a straight line curve here like this. Okay, when I will put here y is equal to h by 2, when I will put y is equal to h by 2, so it will become h by 2, it will get cancelled here to 2, and this is will become h minus h, it will become 0. Means at the center of the between these two plates, the shear stress value will be 0. Shear stress काय असेल त्या ठिकाणी 0 असेल, and it will be maximum at this point. If I put y is equal to 0, this whole quantity will become 0, and this will be the maximum value of shear stress. Okay, so tau max, how to get the maximum shear stress? In this equation, just put y is equal to 0, then you will get this equation minus del P upon del x into h by 2. Okay, so note down these two equations in your notebook. I have written this equation for the velocity distribution. I have written the title there. If not, write down there: flow of viscous fluid between two parallel plates. And there, write down this equation, velocity distribution equation. U is equal to minus 1 upon 2 mu del P upon del x into hy minus y square. Everyone have written this? Next, we will move ahead, write down this shear stress distribution equation. Tau is equal to minus 1 upon 2 del P upon del x into h minus 2y. tau max, value of tau max means maximum shear stress कुठं असतो? Maximum stress will be at the wall of the pipe. So tau max, it can be represented by tau max, or sometimes it is written as tau 0 also. So it is the maximum shear stress at y is equal to 0. So tau 0 is equal to, in this equation, if I put y is equal to 0 here, this will become 0 and I will get this equation. Minus del p upon del x into h by 2. Okay, should we take the next slide? Next is the maximum velocity. Equation for the maximum velocity, u is equal to u max is equal to minus 1 upon 8 mu del p upon del x into h square. This equation is again similar to the or analogous to the maximum velocity for the pipe flow. Pipe flow मध्ये पण अशाच पद्धतीचे एक इक्वेशन आपण त्या ठिकाणी पाहिलेली आहे. Open your page, back pages, and see there what is the equation for u max. Can anyone remember what is the equation for u max? Have you written there? Okay, write down this equation. U max is equal to minus 1 upon 8 mu del p upon del x into h square. The ratio of maximum velocity to the average velocity. Again, same equation we have seen there. Analogous equation for the pipe flow, and there we have seen that u max is equal to u max by u bar, that is the average maximum velocity to the average velocity, is equal to 2. U max is equal to twice the average velocity. This is the equation that we have seen for the pipe flow. And what is the equation here? U max by u bar is equal to 3 by 2, or you can write like this also. U max is equal to 1.5 times of the average velocity. Okay, you can note it down like this. U max is equal to 1 upon 1.5 u bar. Next, drop of pressure for a given length of pipe. There, for the pipe flow, we have written the equation named as Hagen-Poiseuille equation. Okay, Hagen-Poiseuille equation that we have seen there. What was the equation? HF is equal to P1 minus P2 upon rho z is equal to is equal to what? Pipe flow static equation 32 mu u bar L upon rho z d square, where d is the diameter of the pipe. But here we are finding the drop of pressure head between the two parallel plates, fixed plates. So the equation, instead of diameter, here you will get the distance between the two plates, that is h. Okay, that change we have to do here. And instead of 32, we have here 12. This equation can be used for finding the drop of pressure head. Sometimes they will ask you find out what is the difference in the pressure or pressure loss between 2 points. At that time you have to use this equation. Here if you see, this can be cancelled and you will get P1 minus P2 is equal to, the equation can be written as 12 mu u bar L divided by h square. This equation, it can be written for the loss of head or the pressure difference. So everyone written this formula in your notebook. Now we are going to solve one or two problems based upon this. Is it over, everyone? Now let us write down the problem. Water at 15 degree flows between two large parallel plates. Water at 15 degree flows between two parallel plates at a distance of 1.6 mm apart. Determine the maximum velocity second, pressure drop per unit length, and third, the shear stress at the walls of plates. Shear stress at the walls of plates means tau max we have to find, or tau zero. If the average velocity is 0.2 meter per second, average velocity means u bar, that is 0.2 meter per second. The viscosity of water at 15 degrees Celsius is, now mu value is given 0.01 poids. Okay, so first of all, write down the given things. Distance between parallel plates is given 1.6 mm. Convert to meter, that is nothing but h is equal to small h is equal to 1.6 mm. That is nothing but 1.6 into 10 to the power minus 3 meter. Mu is given 0.01 poids divided by 10, you will get 0.001 Newton second per meter square. Average velocity u bar is given, u bar is equal to 0.2 meter per second. Average velocity u bar is equal to 0.2 meter per second. Now what is asked? Find the maximum velocity is the first question. So how to find the maximum velocity? What is the formula? U max is equal to 1.5 or 3 by 2 into h. So total h is given to us. 1.5 into u bar is the equation. So u max is equal to 1.5 into u bar. U bar is given in the problem, that is 0.2. So the answer we have got here as maximum velocity u max is equal to 10. U max is equal to 0.3 meter per second. Then next comes the second question, pressure drop per unit length. How to find out it? We have seen the equation for the pressure drop, head loss, that is HF is equal to P1 minus P2 upon rho z is equal to 32. That was for the pipe, and for this plates, HF is equal to P1 minus P2 upon rho z is equal to 12 mu u bar L upon rho gh. So here in this formula, rho g you can cancel because it is asked to find out the pressure drop. So we can write down the formula as P1 minus P2. This formula you can write. I have found this P1 minus P2. Now, what will be the unit of P1 minus P2? It is per unit length. So the unit will be Newton per meter square for the pressure drop, and for the length per meter length, that we have to write down there. Newton per meter square per meter length. Next, write down the shear stress at the walls. Find out shear stress at the walls. We have written the formula for shear stress. Two formulas we have written. One formula for the normal shear stress distribution, and second formula we have seen for the maximum shear stress, that is tau max. To remember, you can note down that formula. If you don't remember, that formula is here. This is the shear stress distribution equation, and this is the maximum shear stress. Tau is equal to minus 1 upon 2 del P upon del x, h minus 2y. Tau max is equal to minus del P upon del x into h by 2. This is the equation. The same equation we have to use here. Del P upon del x so that you have found here, you can put this value inside this equation, minus half into h. And in this way we can find tau zero value. Second question, calculate first the pressure gradient along the flow. calculate the pressure gradient along the flow. Second, average velocity, and third, the discharge for an oil of viscosity 0.02 Newton second per meter square, flowing between two stationary parallel plates 1 meter apart, 1 meter wide. Yes, the discharge for an oil of viscosity 0.02 Newton per second, Newton second per meter square, flowing between two stationary parallel plates 1 meter wide, maintained 10 mm apart. The velocity midway between the plates is 2 meter per second. The velocity midway means it is the velocity at the center of the distance between the two parallel plates. That is nothing but u bar is given. So first of all, write down the given things. What is given? If you go on reading from the first line, then you will get their viscosity. Mu is given, mu is equal to 0.02 or 0.2 Newton. Then comes the width 1 meter wide, and B, that is B is equal to 1 meter, and small h is equal to 10 mm is 0.01 meter, and u bar is equal to u max is equal to, not u bar, u max is equal to 2 meter per second. Velocity will be maximum at the center or midway. So let us first find out pressure gradient. Pressure gradient, what is formula for pressure gradient? Umax is known to us, so we can use the equation of Umax. Umax is equal to minus 1 upon 8 mu dv upon dx into h. By using this formula, put the value of Umax. Here put the value of Umax, put the value of mu, put the value of EH. You will get the value of dp del p upon del x, and that is equal to minus 3200 Newton per meter square per meter. Minus sign indicates what? Pressure gradient is decreasing. Average velocity. We have the relation between maximum velocity and average velocity. That relation is Umax is equal to 1.5 U bar. So Umax is known to you. Put the value of Umax in the equation and find what is the value of U bar. Next task is to find the discharge. Discharge is nothing but average velocity multiplied by cross-sectional area. What is the area of flow? area of flow is nothing but it is width into height into u bar, that is velocity, average velocity. So we get here the value of q. Putting this value in this equation, 1 is the b, 0.01 is the h, and this is u bar. We will get the value of discharge. In this way we have to solve this problem. Do it fast. Is it over? So viscous flow is this, that part is over here. Now we are moving toward the next point, that is turbulent flow from this unit. Okay, we have what we have studied in the viscous flow. In viscous flow we have studied how the flow takes place through the pipe, viscous flow takes place through the pipe and through the parallel plates, right? And we have seen the Reynolds experiment also there. Here now we will let us understand the turbulent flow. In case of laminar flow, the loss of pressure head was found to be proportional to the velocity. ओके, हाउ हेड लॉस आपण त्या ठिकाणी कसं बघितलं होता, पाईप मधून जर फ्लो होणारा जो फ्लो आहे, पाईप मध्ये जो हेड लॉस आहे HF इज इक्वल टू आपण इक्वेशन लिहिली P1 मायनस P2 डिवाइडेड बाय रो Z इज इक्वल टू 32 म्यू U बार L डिवाइडेड बाय रो Z D स्क्वेअर, हे आपण इक्वेशन बघितली. तर या ठिकाणी U ची पॉवर किती आहे? U बार म्हणजे ॲव्हरेज व्हेलॉसिटी, ॲव्हरेज व्हेलॉसिटीची पॉवर आहे 1, राईट? So here we found that the velocity, that head loss of pressure head or head loss is directly proportional to the velocity. But in case of turbulent flow, the scientist Reynolds, he has observed that what he has observed, that loss of head is proportional to the approximately proportional to the square of velocity. So velocity is a square, velocity की power या ठिकाणी square, more exactly the loss of head HF, it is directly proportional to the v to the power n. He actually equation आहे, and where the power of n is equal to 1.75 to 2.0. So this velocity varies between this value n is equal to, okay. So generally it is taken as square. So here loss of head loss, it varies proportional to the power of 2. Okay, head loss is directly proportional to the V square. Frictional loss in the pipe flow. Now this point we will see. When the liquid is now, why this friction loss in the pipe flow it will takes place? It is takes place because of the viscosity. Due to the viscous nature of the fluid, viscosity मुळे काय होतं त्या ठिकाणी, velocity gradient या ठिकाणी स्टेबिलिटी होतो. सगळ्यात खालची जी लेयर असतात बॉन्ड at the boundary of the pipe wall, that velocity at that layer will be velocity will be equal to 0. त्या ठिकाणी जी velocity असते ते काय असते, 0 असते. आणि जसं आपण एक लेयर दुसरी लेयर वरती जाईल तसे या ठिकाणी velocity वाढत जाते, आणि ते it reaches to the maximum velocity at the center of pipe, and then again it will go on decreasing. And आपल्याला अशा पद्धतीने या ठिकाणी velocity profile पाहायला भेटतो. That velocity profile, we have seen that it was parabolic in nature for the viscous flow, right? आणि ह्या velocity gradient जो या ठिकाणी तयार होतो, ह्या velocity gradient मुळेच त्या ठिकाणी shear stress पण जनरेट होतात. Shear stresses will be generated, and head loss also takes place because of this. Okay, so the viscosity is the main cause for the head loss due to friction. Okay, so this viscous action causes the loss of energy, which is usually known as frictional loss. त्याला आपण काय म्हणतो, frictional loss म्हणतो, HF. Okay, next, how to get that head loss due to friction in the pipe. So to get this head loss due to friction in the pipe, various scientists have done experiments and they have derived the formulas, right? Out of that formulas, one formula is the Darcy Weisbach equation. That this equation is used for finding the head loss due to friction, and this equation is HF is equal to 4 FL square upon 2 ZD. Okay, 4 FLV square upon 2 ZD, where this F is coefficient of friction, L is the length of pipe, V is the average velocity of flow, G is the acceleration due to gravity, and D is the diameter of the pipe. Okay, and we are going to see this derivation in details in the next point. Okay, ह्याची आपण derivation त्या ठिकाणी बघणार आहोत. This equation is known as Darcy Weisbach equation. Sometimes this equation can be written like this also. Okay, instead of 4F, they will write just F. When it is written just F here, this F is called as the friction factor. त्या F ला आपण काय म्हणतो, friction factor म्हणतो. ज्यावेळेस त्या ठिकाणी 4f नसतं, फक्त f लिहिलेलं असतं. Sometimes they will write capital F also. So this F is nothing but friction factor. So this thing we have to keep in mind. Expression for coefficient of friction in terms of shear stress. In for the turbulent flow, expression for the shear stress. Expression for the coefficient of friction F. How we can find the coefficient of friction in turbulent flow? So at that time we have to we can use this equation. F is equal to tau 2 tau 0. Tau 0 is nothing but it is the maximum shear stress, or you can write here tau max also. Maximum shear stress divided by rho into v square. Okay, so this is the expression for coefficient of friction in the pipe. Shear stress in turbulent flow. The Newton scientist, he has given the equation to find the shear stress. Okay, in case of the viscous flow or laminar flow. Laminar flow मध्ये shear stress काढण्यासाठी Newton has given the equation, and that equation we have studied. Tau is equal to mu into du by dy. हे expression आपण त्या ठिकाणी शिकलो. Where this tau can be written as tau v also, viscous shear stress. Okay, this mu is nothing but it is the dynamic viscosity, u is the velocity, and y is the distance between two plates, or we call it as a velocity gradient. Okay, similarly the scientist J. Bosines, this scientist, he has given the equation for shear stress in the turbulent flow. Newton ने कसा दिलता? Newton has given the shear stress equation for the viscous flow. Similarly, this Bosines, he has given the equation for shear stress in the turbulent flow, which is given like this: tau T is equal to eta. Okay, this is pronounced as eta into du bar upon dy. This expression he has given, where tau T is nothing but it is the shear stress due to turbulence. Okay, turbulence will create another shear stress. Then this eta is nothing but it is the eddy viscosity. How viscosity la काय म्हणायचं? Eddy viscosity. And what is this du by dy? Du bar dy, it is the velocity gradient. The ratio of, जसं आपण या ठिकाणी रेशियो घेतो mu upon nu is equal to what? Nu is equal to mu upon rho. So kinematic viscosity is nothing but it is the dynamic viscosity to the weight density. Similarly, here if we take the ratio of eta, that is eddy viscosity, to the density, then it is known as kinematic eddy viscosity, and it is expressed as or denoted by letter epsilon. Okay, it is denoted by letter epsilon. So I can write here epsilon is equal to eta divided by rho. So या ठिकाणी nu is equal to mu upon rho. So या ठिकाणी eta epsilon is equal to eta divided by rho. This equation you can take. This eta is nothing but here it is the turbulent viscosity or eddy viscosity. त्याला काय म्हणतो आपण? Eddy viscosity eta. And what is this epsilon? So epsilon is nothing but it is kinematic eddy viscosity. Kinematic eddy viscosity. Okay. So this equation is used for finding the shear stress in the shear stress due to turbulence, and this expression is used for finding the shear stress due to the viscosity in the viscous flow. Okay, and if you collectively take, if the shear stress due to the viscous flow is also considered, दोन्ही जर आपण या ठिकाणी कन्सिडर केले तर आपल्याला इक्वेशन असे लिहिता येईल: shear stress, total shear stress is equal to shear stress due to the viscous force and shear stress due to the eddy force or the due to turbulence, shear force due to turbulence. या दोन्हीचं आपण या ठिकाणी ऍडिशन करू शकतो. Then we can write this equation as mu into du by dy, where this is the viscous shear stress due to the viscous flow, and instead of this tau t we can write here eta into du bar upon dy. Okay, so this expression it can be written like this. This is the expression for total stress to find the total stress. If the flow is viscous flow, in that case the value of eta will be 0. ज्यावेळेस टर्ब्युलंट फ्लो नसतो, फक्त विस्कस फ्लो असतो, त्यावेळेस हा पार्ट कम्प्लिटली काय होतो, 0 होतो, कारण इटा विस्कॉसिटी, दिस एडी विस्कॉसिटी विल बिकम 0, राईट. म्हणजे हे पूर्ण 0 होऊन जाईल आणि आपल्याला हे फक्त इक्वेशन या ठिकाणी भेटेल. अँड फॉर द अदर केसेस वी नीड टू फाइंड आउट द व्हॅल्यू ऑफ दिस इटा, and this value of eta is 1000 times, nearly 1000 times more than this particular dynamic viscosity. Okay, to find shear stress in turbulent flow, equation 10.7 is given by the Bozinski's use, but as the value of eddy viscosity cannot be predicted, it is very difficult to predict the value of eddy viscosity. This equation has the limited use. The equation use जे आहे ते खूप limited आहेत. Which equation? Bozin's equation. Okay, to find this shear stress due to the turbulence. Okay, then other scientists have worked on it. Then Reynolds has given in 1886, he has develop an expression to find expression for turbulent shear stress between the two layers of the fluid at a small distance apart, which is given as tau is equal to rho into u dash into v dash. What is this u dash v dash? U dash v dash is nothing but it is the fluctuating component of velocity in the direction of x and y due to the turbulence. Okay, वेलोसिटी जी आहे y डायरेक्शन मध्ये असणारी वेलोसिटी आहे u डॅश, आणि वर्टिकल ह्या v डायरेक्शन मध्ये असणारी वेलोसिटी आहे x डायरेक्शन मध्ये असणारी u डॅश, y डायरेक्शन मध्ये असणारी v डॅश, and these velocities are fluctuating continuously. Okay, fluctuating component of the velocities in the direction of x and y due to turbulence. As this u dash and v dash are varying, and hence tau will also vary. As these values are varying, this tau will also what will happen? It will vary. Hence, to find the shear stress, the time average on both sides of the equation is taken. मग हे इक्वेशन अप्लाय करण्यासाठी काय करतो आपण, टाइम ॲव्हरेज व्हॅल्यू या ठिकाणी घेतली जाते, बिकॉज इट इज कंटिन्युअसली फ्लक्च्युएटिंग. सो ॲव्हरेज व्हेलोसिटी टाइम ॲव्हरेज करून त्याची त्या ठिकाणी व्हॅल्यू काढली जाते. फॉर एक्झाम्पल यू डॅश ॲट पर्टिक्युलर टाइम ॲट 9 AM u dash is let us say 10 meter per second, and after 9:05 or just between 9:01 it will be 11 meter per second. Then it again fluctuates and it will go to 9 meter per second. Okay, at 9:02. So we have to do the averaging of these three velocities. Time average we have to do. We have to add this value, then divided by 3. You will get the time average velocity of that. And after finding the average velocity, you can use this equation to get the average value of tau. Okay, turbulent shear stress given by this equation is known as the Reynolds stress. Okay, this tau bar is known as the Reynolds stress equation. Again, this average velocity finding, the task is very difficult. U dash v dash bar, it is difficult task to, the shear stress can only be calculated if the value of u dash v dash is known, but it is very difficult to measure u dash v dash bar. Okay, to overcome this difficulty, now the Prandtal is another scientist, he worked on it, and here he has proposed a theory which is called as the Prandtal mixing length theory. त्यांनी काय केलं? Prandtal mixing length theory दिली for the turbulent shear stress. And what is that Prandtal mixing length theory? So that we will see. According to the Prandtal, the mixing length L, he has considered some distance L, is that distance between two layers in transverse direction such that the lumps of the fluid particles from one layer would reach the other layer and the particles are mixed in the other layer in such a way that the momentum of the particles in the direction of the x is same. Okay, आता दोन लेयर आहेत, त्या दोन लेयर मध्ये जो अंतर आहे हे त्यांनी अंतर जे आहे this distance is called as the Prandtl mixing length in such a way that the particles from this particular layer they can go here and this particle from this layer they may also come here, but the direction of the momentum will be same for these both layers. त्या दोन्ही लेयर साठी the momentum जो आहे in x direction it will be same. So here you can see particles are mixed in other layer in such a way that the momentum of the particles in the direction of x is same. So the momentum in the x direction will be same. He also assumed that the velocity fluctuation in x direction, that is u dash, is related to the mixing length L. So the in x direction मध्ये असणारी जी velocity आहे u dash, it is related to the mixing length this L, ह्या length ला related आहे, and he has given the equation u dash is equal to L into du by dy. Okay. Similarly, the v dash, the fluctuating component of the velocity in y direction, is of the same order of magnitude as u dash, and hence v dash also he has given the equation is equal to L into du by dy. म्हणजेच काय, या दोन्हीचं इक्वेशन हे नियरली सेम आहे. Then and now instead of this u dash and v dash, this equation आपण वरती पाहिलेली आहे, tau bar is equal to rho u dash v dash bar. Now instead of this he has put this values there, so you can see here instead of u dash v dash bar L into du by dy, L into du by dy, these values have been put there. And this L it will become L square, and this du by dy it will become its square. So he has put these values instead of this. Now he has put this L square into du by dy square value there in that equation, and here you can see he has written the equation in this form. Now it is easier for finding the value of average shear stress. Tau bar is equal to rho, that rho was already there, L square into du by dy bracket square. Okay, in this way the value of shear stress is obtained. Thus the total shear stress at the point in the turbulent flow is the sum of the shear stress due to the viscous shear and turbulent shear, and can be written as tau bar is equal to mu into du by dy plus, so this was the turbulent shear stress. Okay, the total shear stress if you want to find, then you can write tau bar is equal to, this is the viscous shear stress and this is the turbulent shear stress. या दोन्हीची या ठिकाणी ऍडिशन केली. ठीक आहे, and we got here the value tau bar. But the viscous shear stress is negligible except the near the boundary. हा जो viscous shear stress जो असतो ना, तो जो कुठल्याही लिक्विड मटेरियलचा जो बाउंड्री असते, त्या बाउंड्रीच्या जवळ या ठिकाणी within the boundary layer this viscous shear stress is प्रिडॉमिनंट म्हणजे जास्त असतो. अपार्ट फ्रॉम दिस बाउंड्री लेअरच्या बाहेर या ठिकाणी टर्बुलंट शिअर स्ट्रेस हा त्या ठिकाणी जास्त असतो. ओके, सो दिस इक्वेशन 10.13 is used for most of the turbulent fluid flow problems for determining shear stress in the turbulent flow. ओके, म्हणजे ज्यावेळेस टर्बुलंट फ्लो असतो त्या टर्बुलंट फ्लो मध्ये दोन्ही टाईपचे शिअर स्ट्रेस तुम्हाला पाहायला भेटतात. नियर द बाउंड्री लेअर देअर वी विल हॅव द shear stress due to the viscous force, viscosity, and apart from that, in the pipe away from the boundary layer, the shear stress will be due to the eddy viscosity, that is eta. And here, what is the meaning of hydrodynamically smooth and rough boundary, that we will see. Okay. Now, if you observe any pipe, though we observe the pipe as a smooth material, कुठलाही आपण जर पाईप घेतला, मेटल पाईप असेल, पीव्हीसी पाईप असेल, we observe it as a smooth one, but if you look through the microscope मधून जर आपण पाहिलं तर आपल्याला त्या ठिकाणी अशा प्रकारचे अंड्युलेशन्स पाहायला भेटतात. ठीक आहे, त्या सरफेस वरती मेटल सरफेस असेल किंवा कुठलाही सरफेस त्याच्यावरती आपल्याला अशा पद्धतीचे अंड्युलेशन्स हे त्या पाईपच्या सरफेस वरती आपल्याला पाहायला भेटतात. ठीक आहे, आणि याच्यामुळे काय होतं त्या ठिकाणी this irregularities, this is called as the irregularities. Let k is the average height of the irregularities projecting from the surface of the boundary. ही average height त्यांनी घेतली. काही ठिकाणी ही हाईट जास्त आहे, काही ठिकाणी कमी आहे. ठीक आहे, या ठिकाणी जास्त आहे, परत कमी आहे. So average value is the k value. They have taken average height of the irregularities projecting from the surface. ठीक आहे, surface of the boundary as shown in figure. If the value of k is large for a boundary, then the value of k is large. If this value of k is large for the boundary, then boundary is called as the rough boundary. काय म्हटलंय? If the value of k is large for the boundary, then the boundary is called as the rough boundary, and if the value of k is less than the boundary, then it is called as the smooth boundary. म्हणजेच काय, ही जी लॅमिनर सब लेअर आहे याच्या खाली द फ्लो इज विस्कस फ्लो. ही जी लॅमिनर सब लेअर पेक्षा म्हणजेच हा जो डेल डॅश आहे, डेल डॅश, या डेल डॅश पेक्षा जर के ची व्हॅल्यू कमी असेल तर त्या केसमध्ये आपण त्याला म्हणतो स्मूथ बाउंड्री, आणि जर के ची व्हॅल्यू ही डेल डॅश पेक्षा जास्त असेल देन वी कॉल दिस बाउंड्री ॲज अ रफ बाउंड्री. ठीक आहे, लॅमिनर सब लेअर म्हणजे काय, द लेअर बियॉन्ड विच द फ्लो विल बी टर्बुलंट फ्लो हिअर, अँड या ठिकाणी फ्लो असेल लॅमिनर फ्लो. ओके, याच्या खाली लॅमिनर फ्लो आहे, वरती टर्बुलंट फ्लो आहे. या ठिकाणी वरती टर्बुलंट फ्लो आहे, खाली लॅमिनर फ्लो आहे. But the value of k is larger than the laminar sublayer, so this is the rough boundary, and this is called as the smooth boundary. This is the classification of rough and smooth boundary based on the boundary characteristics. Boundary चे characteristics वरती हे depend करेल whether the boundary should be called as a smooth boundary or rough boundary. But for the proper classification, the flow and fluid characteristics are also to be considered. Proper classification करायचं असेल तर आपल्याला त्या ठिकाणी फ्लो आणि फ्लुइड कॅरेक्टरिस्टिक्स हे आपण त्या ठिकाणी आपण कन्सिडर केले पाहिजे. But here just understand what is the meaning of smooth boundary and rough boundary. Variation of coefficient of friction. Coefficient of friction is nothing but f. So in case of laminar flow, in case of viscous flow, we have seen that the value of f, it was varying with the Reynolds number. And what was the equation? There we have seen that this f is equal to 16 upon Re. This was the expression that we have seen for the coefficient of viscosity, relation between the coefficient of viscosity and Reynolds number. How we can find that was in for the viscous flow. This it also can be expressed in terms of friction factor. So we have to multiply it by 4. So it will become 54 divided by RE. Okay, so this is the friction factor in that case. Now here variation of wave for the turbulent flow, how it varies. For the turbulent flow, the coefficient of friction is a function of Reynolds number and K by D ratio. त्या ठिकाणी लॅमिनर फ्लो मध्ये इट वॉज द फंक्शन ऑफ ओनली RE. Reynolds numberचं फंक्शन होतं, but in case of turbulent flow, now this F is a function of Reynolds number as well as it is the function of relative roughness. This K by D is nothing but it is called as the relative roughness. For the relative roughness in the turbulent flow, the boundary may be smooth or rough, and hence the value of F will be different for these boundaries. Okay, so relative roughness is important. F for smooth pipe. Ata depending upon the type of boundary, smooth boundary or rough boundary, the equation for the F it will vary. For the smooth boundary, the equation for the F is given as F is equal to 0.0791 divided by RE raised to 1 by 4. This is the expression for smooth boundary. For the rough boundary, the expression is given as 1 upon under root of 4F is equal to 2 log 10 R by K plus 1.74. So these equations we should note down in your notebook. Okay. So there are derivation on each these particular equations, but we are not going in that much details. We don't have that much time to see the derivation of all the things here. So you can note down this equation in your notebook from shear stress from the turbulent flow here. Expression for head loss. This expression we are going to see afterwards. So don't write this. Write just this expression for coefficient of friction in terms of shear stress, or directly we will come here. Note down these equations. Write down this sentence. This one.
Now I like
and then this one. Sanket. So now we will see the next point: loss of energy or head, loss of head in a pipes. So now this may be the familiar part to you. You might have heard about this minor losses, major losses somewhere. Have you heard this? Head loss due to friction. As you are the first year student, you might not have listened regarding this. So let us understand this and we will move ahead. Write down the title: loss of energy or head loss in the pipe. Have you written these titles there in your notebook? Just write down at least titles there in the notebook. Turbulent flow, title है turbulent flow. Then write down there frictional loss in the pipe flow, title. Expression for head loss due to friction. हे आपण नंतर बघणार आहोत. हे राहू दे. Shear stress in the turbulent flow. Write down the title: shear stress in turbulent flow. Then expression, Reynolds expression for turbulent shear stress. Write down the title: Reynolds expression for turbulent shear stress. You can note down this equation. Tau bar is equal to rho u dash v dash bar. Reynolds expression for turbulent shear stress. Then next write down the title, Prandtal mixing length theory. Prandtal is the name of scientist who has even proposed this theory in 1925. Prandtal mixing length theory for turbulent shear stress. Prandtal mixing length theory for turbulent shear stress. Then you can note down this equation. Tau bar is equal to mu into du by dy plus rho L square into du by dy bracket square. Then write on the title, hydrodynamically smooth and rough boundaries. Hydrodynamically smooth and rough boundaries. Next, variation of coefficient of viscosity. Variation of coefficient of viscosity. Note down these two formulas. Write on the title there. For F for smooth pipe, and write down this formula. F for rough pipes, write down this formula. Wait fast. For
Yes, sir.
write on the title, loss of energy or loss of head in pipes. Loss of energy or loss of head in the pipes. Have written. So let us now understand what are the various types of losses that takes place in the pipe fluid. Okay. When fluid is flowing through the pipe, the fluid experiences some resistance due to which some of the energy of the fluid is lost. Fluid ची जी energy possess केलेली आहे, that energy is get lost, and this loss of energy is classified in two categories. We can classify the loss, head loss or the loss of energy. This we call loss of energy, or we also call it as a head loss. Okay, हे दोन शब्द आपण वापरतो, head loss किंवा loss of energy. तर This loss of energy or the head loss, it can be classified into categories. One is called as the major energy losses and second one is called as the minor energy losses. Okay, or simply we call it as a major losses, major head loss and minor head losses. हे दोन कॅटेगरी मध्ये करतो. हे मेजर हेड लॉस कशामुळे होतात? मेजर कशामुळे म्हटलं जाते ना? बिकॉज द क्वांटिटी proportion of this head loss due to this losses, it is very large in number, large in quantity as compared to the head loss due to this minor losses. यांच्यामुळे होणारा जो लॉस आहे तो खूप कमी आहे आणि यांच्यामुळे होणारा जो लॉस आहे तो खूप जास्त आहे. ठीक आहे. तर हा जो मेजर हेड लॉस आहे, दिस ऑकर्स ड्यू टू द फ्रिक्शन. ओके, त्यामुळेच हा जो मेजर लॉस आहे, इट इज ऑल्सो समटाइम्स इट इज ऑल्सो कॉल्ड एज हेड लॉस ड्यू टू फ्रिक्शन. हेड लॉस ड्यू टू फ्रिक्शन or HF. It is generally related by HF also. And it is given by formulae or it is calculated by formulas like Darcy Weisbach equation. Okay, वरती आपण जे इक्वेशन बघितली होती ती आता आपण या ठिकाणी बघणार आहोत डिटेल मध्ये. It is given by the Darcy Weisbach equation and this can be obtained by using Chase's formula. These are the two formulas with the help of which we can find out the major losses. Okay, minor losses मध्ये या ठिकाणी काय काय येतं? हेड लॉस ड्यू टू दी सडन एक्सपान्शन ऑफ द पाईप. म्हणजेच काय ते आपण डिटेल मध्ये पुढे बघणारच आहोत. हा छोटा पाईप आहे आणि हा परत मोठा पाईप आहे. अचानक जर या ठिकाणी असे सडन एक्सपान्शन झालं असेल, पाईप वाढला असेल, त्या ठिकाणी जो होणारा लॉस आहे दॅट इज कॉल्ड एज द हेड लॉस ड्यू टू सडन एक्सपान्शन. सडन कॉन्ट्रॅक्शन मध्ये काय होतं? मोठ्या पाईप मधून छोट्या पाईप मध्ये पाणी जाताना जो होणारा लॉस आहे दॅट इज कॉल्ड एज द हेड लॉस ड्यू टू सडन कॉन्ट्रॅक्शन. ठीक आहे. देन हेड लॉस ड्यू टू द बेंड इन द पाईप. पाईप जर पाईपला बेंड असतात, ओके, ज्यावेळेस टर्न करतो पाईप आपण त्यावेळेस त्याला त्या ठिकाणी आपण बेंड्स, एल्बोज वगैरे वापरतो. त्याच्यामुळे जो होणारा लॉस आहे दॅट इज कॉल्ड एज द हेड लॉस ड्यू टू बेंड इन द पाईप. नेक्स्ट इज द पाईप फिटिंग्स. हेड लॉस ड्यू टू पाईप फिटिंग्स. Different types of pipe fittings like valves are there. Okay, pipe joiners are there. जॉईन करण्यासाठी वापरतो आपण कपलिंग्स. ओके, किंवा वॉल्स बसवले असतात त्याच्यामुळे होणारा लॉस आहे. सो दॅट इज कॉल्ड एज द हेड लॉस ड्यू टू पाईप फिटिंग्स. अँड लास्ट वन इज द हेड लॉस ड्यू टू एन ऑब्स्ट्रक्शन इन द पाईप. म्हणजे एखाद्या पाईपमध्ये एखादा काही अडथळा वगैरे असेल बरेच, ओके, तर त्याच्यामुळे होणारा जो लॉस आहे हेड लॉस, दॅट हेड लॉस इज कॉल्ड एज द head loss due to obstruction. So all these collectively they are called as the minor losses. Why they are called as the minor losses? Because their quantity is very small as compared to the major losses. जर पाईप ची लेंथ खूप कमी असेल, in that case we can neglect these minor losses. We have to consider the minor losses. आणि पाईप ची लेंथ खूप मोठी असेल त्या केसमध्ये मेजर लॉसेस खूप जास्त प्रमाणामध्ये जर असतील तर मायनर लॉसेस आपण त्या ठिकाणी निग्लेक्ट करू शकतो. ठीक आहे. बट फॉर द शॉर्टर पाईप वी हॅव टू कन्सिडर दिस मायनर लॉसेस ऑल्सो. ठीक आहे. नाउ वी विल सी इन डिटेल्स अबाउट दिस मेजर लॉसेस अँड मायनर लॉसेस. हेड लॉस ड्यू टू फ्रिक्शन. ओके, फ्रिक्शनल लॉस इन द पाईप फ्लो किंवा मेजर लॉस जो आपण म्हटलेला आहे तो आपण आता या ठिकाणी बघणार आहोत. When the liquid is flowing through a pipe, the velocity of the liquid layer adjacent to the pipe wall is 0. जे सगळ्यात खाली जी लेअर असते ते आपण तुम्हाला अगोदर मी सांगितलेलं आहे. पाईपला चिटकून जी त्या ठिकाणी लेअर असते, या ठिकाणी असेल किंवा या ठिकाणी असेल, त्या लेअरची वेलोसिटी काय असते? 0 वेलोसिटी असते. v इज इक्वल टू 0. अँड ती वेलोसिटी काय होते? जसं आपण वरती जाईल, एका लेअर पासून दुसऱ्या लेअर असं वरती जाईल, तशी ती वेलोसिटी काय होते? वाढत जाते. सेंटरच्या ठिकाणी सगळ्यात जास्त असते आणि परत कमी होत या ठिकाणी 0 होते परत. ठीक आहे. The same thing has been mentioned here. Liquid layer adjacent to the pipe wall is 0. The velocity of the liquid goes on increasing from the wall and thus velocity gradient and hence shear stress is produced in the whole liquid due to viscosity. मग या ठिकाणी काय होतं? विस्कॉसिटी मुळे या ठिकाणी शिअर स्ट्रेस जनरेट होतो त्या वेलोसिटी प्रोफाइल मुळे. ठीक आहे. And this viscous action causes the loss of energy which is usually known as frictional loss. मग हा जो विस्कोसिटी मुळे होणारा जो लॉस आहे त्याच्यामध्ये शिअर स्ट्रेस जनरेट होतो आणि हेड लॉस होतो, त्या लॉसलाच काय म्हटलं जातं, हेड लॉस ड्यू टू फ्रिक्शन or frictional loss असं त्याला त्या ठिकाणी आपण म्हणतो. On the basis of his experiments, William Froude, okay, William Froude, he has given the some laws which are called as laws of the fluid friction, okay, for the turbulent flow. परीक्षेमध्ये याच्यावरती एक प्रश्न विचारला जाऊ शकतो. What are the laws of fluid friction for the turbulent flow? So according to William Froude, some call it as a Froude, okay, or some call it as a Froude. According to this William Froude, he has given different laws of fluid friction. So this laws of fluid friction has been given here. We will read it one by one. We will understand it one by one. Okay, the frictional resistance for the turbulent flow is proportional to the v to the power n. Okay, the frictional resistance it is proportional to the v to the power n, where n varies from 1.5 to 2. So that's point we have seen in the previous slide. Okay, in case of turbulent flow, the head loss hf, or this value of f, it varies directly to the power of n to the power v to the power n, and that n varies from 1.5 to 2. This frictional resistance is proportional to the density of the fluid. Density जेवढी जास्त असेल तेवढा त्या ठिकाणी रेजिस्टन्स हा जास्त असणार आहे. This frictional resistance is proportional to the area of surface in contact. जर क्रॉस सेक्शन एरिया मोठा असेल तर हा पण या ठिकाणी व्हॅल्यू काय होते, वाढते. ठीक आहे, इट इज प्रोपोर्शनल टू द एरिया ऑफ सरफेस इन कॉन्टॅक्ट. इट इज इंडिपेंडेंट ऑफ द प्रेशर. प्रेशर कमी असला काय जास्त असला काय तर याच्यावरती रेजिस्टन्स वरती फरक पडत नाही. इट डिपेंड्स ऑन व्हेलॉसिटी. जर वाढली कमी झाली तर फरक पडतो, व्हेलॉसिटी वरती फरक पडतो, पण प्रेशर वरती फरक पडत नाही. इट इज इंडिपेंडेंट ऑफ द प्रेशर. ठीक आहे. And last one, it depends on the nature of the surface in contact. हा जर सरफेस जो पाईपचा सरफेस जो आहे तो जर स्मूथ असेल तर त्या ठिकाणी होणारा जो फ्रिक्शनल रेजिस्टन्स आहे तो कमी असेल. जर पाईप रफ असेल तर त्या रफ पाईप मध्ये हेड लॉस हा जास्त होतो. इट ऑल्सो डिपेंड्स ऑन द नेचर ऑफ द सरफेस इन कॉन्टॅक्ट. ठीक आहे. So these are the different laws of friction which has been given by the scientist William Froude. Now here we are going to derive an expression for head loss due to friction in pipe. Okay. Here we are going to see the expression derivation for head loss due to friction in pipe, and this equation is also called as Darcy Weisbach equation, that we are going to see it first here, and after that Darcy Weisbach equation we will see Chase's formula for loss of head due to friction in the pipe. Okay, so in this way we are going to move ahead here. So let us start now the derivation for the Darcy Weisbach equation. See, we have to consider the uniform horizontal pipe. जसं आपला कॉमन पाईप असतो पीव्हीसी पाईप वगैरे त्या टाईपचा एक पाईप युनिफॉर्म पाईप पण या ठिकाणी कन्सिडर केलेला आहे, ज्यातून होणारा जो फ्लो आहे स्टेडी फ्लो आहे. सो आता स्टेडी फ्लो इव्हन आपल्याला सगळ्यांना माहित आहे. व्हॉट इज द मिनिंग ऑफ स्टेडी फ्लो? द फ्लो इन विच प्रॉपर्टी लाईक वेलोसिटी, प्रेशर, डेन्सिटी, they do not change with respect to time. So that flow is called as the steady flow, right? And we have considered the two sections, section 1 and section 2 here. दोन सेक्शन आपण या ठिकाणी कन्सिडर केले. सेक्शन 1 च्या ठिकाणी जो प्रॉपर्टीज आहेत जसे की प्रेशर आहे, वेलोसिटी आहे, डेन्सिटी आहे, त्याला आपण या ठिकाणी नोटेशन वापरलं 1, आणि या ठिकाणी जे प्रॉपर्टीज आहेत तर नोटेशन वापरलं 2. त्यामुळे या ठिकाणचा प्रेशर असेल P1, या ठिकाणी असेल P2, या ठिकाणी वेलोसिटी असेल V1, या ठिकाणची वेलोसिटी असेल V2. ठीक आहे, लाईक दॅट नोटेशन्स वी हॅव यूज्ड. The distance between these two particular section, it is considered as length L. Okay, length L is the distance between these two D is the small d is the diameter of the pipe. Okay, या pipe चे diameter या ठिकाणी दिलेले आहे. Then F dash, F dash is the frictional resistance per unit weighted area per unit velocity. Okay, what is this F dash? F dash is frictional resistance. It is the resistance, and the resistance कोणत्या डायरेक्शन मध्ये दाखवेल? जर वेलोसिटी पाणी या डायरेक्शन मध्ये फ्लो होत असेल, वेलोसिटी जर या डायरेक्शन मध्ये असेल, तर रेजिस्टन्स जो फ्रिक्शनल रेजिस्टन्स जो आहे तो त्याच्या अपोजिट डायरेक्शन मध्ये या ठिकाणी ऍक्ट होईल, लाईक दिस. ओके, F dash is the frictional resistance per unit weighted area. Per unit weighted area means त्याचा आतला जो एरिया आहे कशाचा, या पाईपचा जो आतला सरफेस एरिया आहे, दॅट इज कॉल्ड एज द वेटेड एरिया. वेटेड एरिया म्हणजे जो एरिया वेट झालेला आहे, भिजलेला आहे. ओके, म्हणजे पाईपचा आतला पूर्ण एरिया वेट भिजलेला असेल, दॅट इज कॉल्ड एज द वेटेड एरिया पर युनिट वेटेड एरिया. मग हा पाईपचा वेटेड एरिया काय असेल? इट विल बी द सर्कमफरन्स ऑफ द सर्कल, दॅट इज pi d. Pi d is the circumference of circle into length of the pipe. Pipe ची length. So this is called as the weighted area. Per unit weighted area means this per unit weighted area, and per unit velocity. Per unit velocity means what? Per unit velocity. ही जर velocity 1 असेल त्या केस मध्ये हा f dash it will have certain value. Okay. जर परत velocity वाढली तर हा पण या ठिकाणी रेजिस्टन्स पण या ठिकाणी काय होईल? वाढेल. ओके, पर युनिट वेलोसिटी. HF is the loss of head due to friction, or we call it as a head loss due to friction. आणि याची डेरिवेशन आपण या ठिकाणी डिराइव्ह करतो, फाइंड आउट करतो. HF is equal to what? हे आपण डेरिवेशन या ठिकाणी करतो फाइंड. And other parameters at the section 2 are same. ओके, तर नोटेशन 2 वापरलेला आहे. Let us now move ahead. Now, applying Bernoulli's theorem or Bernoulli's equation between section 1 and 2. Bernoulli's equation आपण शिकलेलो आहोत. What is that Bernoulli's equation? If you apply the Bernoulli's equation between two sections, section 1 and section 2, then what can be we write the equation, Bernoulli's equation. Okay, ह्या section 1 मध्ये आणि ह्या section 2 चा total head आपण इक्वेट करतो, right? Bernoulli's equation मध्ये. What is the total head at section 1? Section 1 चा total head आहे P1 upon rho z plus v1 square upon 2z plus z1. What is the total head at section 2? Total head at section 2 is the p2 upon rho z plus velocity head v2 square upon 2z plus datum head, that is z2. राईट. मग हे दोन आपण इक्वेट करायचे. पाईप कसं या ठिकाणी आपण हॉरिझॉन्टल पाईप कन्सिडर केलेला आहे, त्यामुळे या ठिकाणी जो z1 आणि z2 जो आहे त्याची डेटम पासूनची हाईट सेम असेल, त्यामुळे z1 आणि z2 आपण या ठिकाणी कॅन्सल करू शकतो. ठीक आहे. So let us first of all understand this equation. Total head at section 1 is equal to total head at section 2 plus loss of head due to the friction between 1 and 2. याच्यामध्ये लॉस ऑफ हेड पण आपल्याला कन्सिडर करावं लागेल. बर्नौलीज इक्वेशन मध्ये आपण हेड लॉस आपण कन्सिडर करत नव्हतो, मग त्यामुळे त्या ठिकाणी आपण मॉडिफाईड बर्नौलीज इक्वेशन आपण पाहिली होती. बर्नौलीज इक्वेशन मध्ये विस्कॉसिटी आयडियल फ्लुइड साठी इक्वेशन डिराइव्ह केलेली आहे बर्नौलीज इक्वेशन. ओके, त्याच्यामध्ये विस्कॉसिटी कन्सिडर केली नाही, पण ऍक्च्युअली देर इज नो सच फ्लुइड विच डोंट हॅव द विस्कॉसिटी इन ऍक्च्युअल प्रॅक्टिस, राईट. त्यामुळे आपल्याला ती हेड लॉस पण आपल्याला कन्सिडर करावा लागतो. आणि मॉडिफाईड बर्नौलीज इक्वेशन जे असते, मॉडिफाईड बर्नौलीज इक्वेशन काय सांगते आपल्याला? टोटल हेड ऍट सेक्शन 1 इज इक्वल टू टोटल हेड ऍट सेक्शन 2 प्लस HF. दिस इज द मॉडिफाईड बर्नौलीज इक्वेशन. ओके, and this modified Bernoulli equation we have to apply when this fluid will move from this section 1 to section 2. At that time there will be head loss, it is going to occur there due to the viscosity, and this is represented by letter HF. Okay, and that's why we have written this equation like this here. Total head at section 1, what is the total head at section 1? That is P1 upon rho z plus v1 square upon 2z plus z1 is equal to what? Total head at section 2, that is P2 upon rho z plus v2 square upon 2z plus z2 plus HF, that is head loss. हा एवढ्या क्वांटिटीने त्या ठिकाणी हेड कमी झालाय, तो कंपन्सेट करण्यासाठी, इक्वल करण्यासाठी आपल्याला हे HF एवढी व्हॅल्यू याच्यामध्ये या इक्वेशन मध्ये आपल्याला राईट हँड साइडला ऍड करावं लागेल. बरोबर आहे. अँड ऍज पाईप इज हॉरिझॉन्टल, व्हॉट इज गोइंग टू हॅपन? as pipe is horizontal, this Z1 will be equal to Z2. This will get cancelled. हा जो Z1 आहे आणि हा Z2 या ठिकाणी काय होईल, कॅन्सल होऊन जाईल. Z1 will cancel with Z2. Also, the pipe is of the uniform diameter. सेक्शन 1 च्या ठिकाणी जी डायमीटर आहे ती सेक्शन 2 च्या ठिकाणी डायमीटर आहे. सेक्शन 1 च्या ठिकाणी जो एरिया असेल A1, the same area will be there at the section 2, and therefore due to which we can say that velocities also are same at section 1 and section 2. Pipe is of the uniform diameter, so this will also get cancelled, right? This velocity will also get cancelled, and we will get the equation as this P1 upon rho g will come here, this P2 upon rho g will come here, and this HF will come here, and we will get this equation as P1 upon rho g is equal to P2 upon rho g plus HF. ही आपली इक्वेशन या ठिकाणी भेटली. ठीक आहे. Now if I take this P2 upon rho g on this side, left hand side here, then I can write this equation as HF is equal to P1 upon rho g minus P2 upon rho g. And this equation, we know that we have used it many times. HF is equal to P1 minus P2 upon rho g, right? Frictional pressure head difference. Okay, pressure head at section 1 minus pressure head at section 2 is nothing but it is the head loss due to friction. But HF is the head loss due to friction, and hence intensity of pressure will be reduced in the direction of flow by the frictional resistance. Right, intensity of flow will be reduced. या ठिकाणी pressure P1 आणि P2. P1 will be greater than P2. There is a loss in the head. Due to that, pressure is going to decrease there, and that's why P2 value will be smaller as compared to the P1 value. Now this frictional resistance will be equal to, as a frictional resistance side, that will be equal to frictional resistance per unit weighted area per unit velocity, that we have written there F dash. Okay, F dash आपण वरती लिहिलेलं. This is the F dash, frictional resistance per unit weighted area per unit velocity. Now if you multiply this by weighted area and the velocity, then you will get here the frictional resistance. Frictional resistance आपल्या ठिकाणी भेटेल. Velocity square ने multiply करतोय कारण turbulent flow आहे. फ्लो मध्ये त्या ठिकाणी स्क्वेअर velocity स्क्वेअर त्या ठिकाणी आपण बघितलं आहे. लॉ ऑफ frictional law of the flow, that at that time we have seen that. Okay, now I am going to put these values here. This particular thing is nothing but this is F dash. Now frictional resistance is represented by letter F1. Okay, then weighted area is nothing but it is pi dl. What is this pi dl? Pi d is nothing but it is the circumference of the circle, and L is the length between these two, section 1 and section 2. Okay, this is the pipe. आपण सेक्शन 1 आणि सेक्शन 2 असे दोन घेतले. सेक्शन 1 1, सेक्शन 2 2, असे आपण दोन सेक्शन त्या ठिकाणी कन्सिडर केले. जर याचा मग आतला वेटेड एरिया काय येईल? एरिया ऑफ द सर्कल मल्टिप्लाइड बाय लेंथ ऑफ द पाइप, that is pi d L is the weighted area. Then velocity square, that is v square. This is the average velocity that we have to keep in mind, right? Then next, this pi into d is nothing but it is perimeter of the circle. So instead of this it has written as p. P is the perimeter of the, or circumference of the circle, or perimeter we can call it. The forces acting on the fluid between section 1 and 2 are, what are the various forces acting between these two sections, section 1 and 2? The forces that are acting are pressure forces. At section 1 will be P1 into area. P1 is the pressure intensity multiplied by the cross section area. Then pressure force at the section 2 will be equal to P2 into area, that is pressure force at pressure intensity at section 2 multiplied by area, right? And third force, that is frictional force, that is F1, it is acting there. This pressure force P1, it is acting in forward direction. This pressure 2, it is acting in reverse direction, opposite direction, and this F1, it is also acting in this direction. So net force जर आपण या ठिकाणी अंडर इक्विलिब्रियम कंडिशन काय होईल, we can write this equation as F1 is equal to not F1, that is P1 into A area is equal to F1 plus P2 into area. Like this we can write. Or जर हे दोन्ही एका साइडला घेतले तर या ठिकाणी मायनस येईल, या ठिकाणी मायनस येईल, इक्वल टू 0. Like that equation we can write. Resolving all the forces in the horizontal direction we get, you can see here, just now I have written this equation. P1A, it is the force acting in the right side, toward the right. This is acting toward the left, this is acting toward the left, that's why minus minus is equal to 0. Okay, under equilibrium condition, this equation we will get. Now area is common, we can take this a common here, P1 minus P2, we can write here like this is equal to F1. So this will become is equal to F1, right? And what is this F1? F1 is nothing but it is F dash P into L into V square. Okay, हे कुठून आलं तर मागच्या इक्वेशन वरती आपण पाहिलं होतं स्लाइड वरती, या ठिकाणी you can see F1 is equal to F dash P L V square. So that instead of F1 we have put there like this. Then take this area on the right hand side, you will get there P1 minus P2 is equal to F dash upon A. This equation you will get. Now this P1 minus P2, what is this P1 minus P2? हे आपण या ठिकाणी पाहिलं होतं, HF is equal to P1 minus P2 upon rho Z. हे आपण त्या ठिकाणी काढलं होतं. कुठे काढलं होतं? मागच्या स्लाइड वरती, या ठिकाणी पहा. Here you can see. Right. तेच आपण त्या ठिकाणी आता पुट करतोय. P1 minus P2 जो आहे प्रेशर इंटेन्सिटी, त्याच्याऐवजी I will put there this rho Z into HF. Okay. So this I will put there. Okay. You can see here, instead of this rho Z HF, this instead of this P1 minus P2, I have put there as a rho Z HF. So I have put here rho Z HF is equal to F dash PLV square upon A. Understood? Then take this rho Z on this side. So we can write here HF is equal to F dash upon rho Z into P upon A into L into V square. Now in this equation, P upon A is nothing but weighted area upon perimeter upon area. P upon A. So for this P is nothing but it is pi d. Area is nothing but it is pi d square by 4. So this pi d, pi will get cancelled, 1d will get cancelled here, and this 4 will come in the numerator. It will become 4 by d. Okay, instead of P divided by, we can now write 4 by d. Now putting F dash upon rho, हे F dash upon rho जो आहे ह्याच्याऐवजी किती काय केलं, F by 2, where F is known as coefficient of friction. Okay, F dash upon rho च्या ऐवजी त्याने काय केलं, F put केला. This F is nothing but F by 2 put केलं, and where this F is nothing but it is coefficient of friction. या इक्वेशन मध्ये टाकलं. मग इक्वेशन काय झाली, मग HF is equal to हा 4 या ठिकाणी गेला. Okay, 4 F is 2 F by 2, it will come here. This Z will come here in the denominator. Okay, then L V square, this part will be as it is there, and this D it will come here. Okay, and after rearrangement we can write this equation as 4 FLV square upon 2ZD. So HF is equal to 4 FLV square upon 2ZD is our final equation here we have got, where F is the coefficient of friction, right? HF is the head loss due to friction, L is the length of pipe, V is the velocity, average velocity of flow, D is the diameter of the pipe. Okay. Sometimes this equation 4FLV square upon 2GD, it can be written as FLV square upon 2GD. 4F च्या ऐवजी फक्त F जर लिहिला असेल त्यावेळेस समजून घ्यायचं की हा F जो आहे this F is called as the friction factor. Okay, तर आपण काय म्हणतो friction factor. What is the relation between friction factor and coefficient of friction? Friction factor is equal to, it is 4F, the relation. This is the coefficient of friction and this is the friction factor. Okay, so this was about the derivation for the Darcy-Weisbach equation, head loss due to friction. Next is the Chase's formula for the loss of head due to friction in the pipe. So first of all, we will note down this. Write down the title. Loss of energy or head in the pipes, as you have written. Write down this classification. हे जे classification आहे ते तुमच्या notebook मध्ये लिहून घ्या. Major losses, minor losses. Write down this and this also. Okay, I will take your attendance. 10 minutes are there. They are taken your attendance. Is it over? All of you have written this tree diagram. Energy losses, major loss, minor losses.
Yes, sir.
Is it over?
Yes, sir.
Okay. Write down the title, frictional loss in the pipe flow. Frictional loss in the pipe flow. Frictional losses in the pipe flow. Then below that, write down the title, laws of fluid friction. Laws of fluid friction. LAWS, laws of fluid friction. Write out these laws. The frictional resistance for turbulent flow is frictional resistance for turbulent flow is proportional to V raised to n. Proportional to the V raised to n. Where n varies from 1.5 to 2. Second, proportional to the density of fluid. This frictional resistance is proportional to the density of fluid. Third, proportional to the area of surface in contact. Proportional to the area of surface in contact. Next, independent of pressure. Independent of pressure. Last one, dependent on the nature of the surface in contact. Dependent on the nature of the surface in contact. Now, write on the title, expression for head loss due to friction in the pipe. Expression for head loss due to friction in pipe. Draw this diagram. And write down these things. Do it fast. As per the new syllabus, this unit has become very big unit. It is the combination of the two units from the old syllabus, previous syllabus. In the previous syllabus, there were two units separate, unit number 5 and 6. Now these two units, unit number 5 and 6, they are combined together to form this unit number, I think this is unit number 5 in the new syllabus from the second section, first unit. Is it over? Yes.
Sir, 2 minutes.
Now here we are not going to write down all the derivation, just write down the formula. After this, is it over? Write out this final formula. You can write like this also. HF is equal to 4FL square upon 2ZD. Or you can write like this. Here in this formula, you can see there is a v square upon 2g. This is nothing but it is velocity head. That's why they have written like this. Or some question may come in your mind that why this 2 is not cancelled with this 4. After that, write down this expression also. Above equation is called as Darcy-Weisbach equation. Write down there. Above equation is called as Darcy-Weisbach equation. This equation commonly used for finding the loss of head due to friction in the pipe. Sometimes above equation can be written as like this, where F is known as friction factor. Okay, is it over? Now time is over. Let us stop now. लिहून झालं का सगळ्यांचं? Yes. Okay, now I will close the session. Thank you for